Students, in the previous classes, we have discussed about R modules and projective and injective modules. And yesterday we have discussed about finitely generated modules. What do you mean by finitely generated module? Just to let us have some important concepts of the yesterday's class. Let M be a module over a ring R, and M is said to be finitely generated. Capital M is said to be finitely generated if there is a finite subset X of M, a finite subset X of M, such that every element of M is of the form. I told you this is known as linear combination A1 X1 plus A2 X2 so on AN Xn. So if every element alpha belongs to X is of the form A1 X1 plus A2 X2 plus and so on AN Xn, which can also be represented by sigma I is equal to 1 to N AI Xi, then we say that X is finitely generated, and we have seen that every homomorphic image. What do you mean by homomorphic image? Suppose F is a mapping from G to G dash, then F of G is known as homomorphic image, which is F of G, which is a subset of G dash, is called the homomorphic image of group G. What do you mean by homomorphism? If for every A comma B belongs to G, if F of AB is equal to F of A into F of B, for all A comma B belongs to G, then we say that hello? Geeta వాళ్ళ ఇంట్లోనే ఉన్నా చెప్పు ఏమన్నా అర్జెంటా? If F of AB is equal to F of A into F of B, for every A comma B belongs to G, F is a homomorphism. And we have discussed about projective module and injective module. Here, what is the epimorphism? Epimorphism is onto homomorphism is known as epimorphism. One homomorphism is known as monomorphism. If there exists a epimorphism, then it is known as a projective module. And also I have discussed about pre-module also. And what do you mean by a projective module? Let P and M be modules over a ring, or P is said to be projective relative to M, or M projective. If for any epimorphism and a homomorphism, you have F is a epimorphism and G is a homomorphism. For every epimorphism F from M to N, and for any homomorphism F is a mapping from M to N, G is a mapping from P to N. Then there exists G bar such that F circle G bar is equal to G. So this is called a projective module. In same way, you have injective homomorphism, that is a monomorphism, then it is said to be injective module. But here, these homomorphisms play a very important role in commutative algebra. And yesterday, I have discussed about the injective test lemma or the Bayer's criterion. Let R be a commutative ring with identity and I is an R module. Then the following are equivalent. I is injective, I is R injective, and for any ideal J of R and for any R homomorphism G from J to I, there is an element X belongs to I such that G of A is equal to AX for all A belongs to G. Today, as today is the last class, I want to discuss about the famous theorems of 4 theorems of commutative algebra. One is 5 lemma. And the other one is 9 lemma. And then going up theorem and going down theorem. Now, students, listen here. A sequence of R modules. A sequence of R modules and R homomorphisms. A sequence of R modules and R homomorphisms given by so on Mn minus 1 to Mn to Mn plus 1, so on. Here you have Fn minus 1. Here you have Fn is said to be exact. Is said to be exact at Mn if image of Fn minus 1, image of Fn minus 1 is kernel of Fn. What do you mean by kernel? Kernel of a homomorphism is the set of all those elements that are mapped onto identity element. Or you have kernel of F is equal to the set of all x such that Fnx is equal to 0. Actually, this exactness of F, exactness at Mn is equivalent to saying that for any x belongs to Mn, Fnx equal to 0 if and only if Xn is x equal to Fn minus 1y. For some y belongs to M suffix n minus 1. So in the sequel, M tends to 0 or 0 tends to M is a trivial homomorphism. Now let us discuss. See this exact equation. A sequence of R modules and R homomorphisms is said to be exact at Mn if Fn image of Fn minus 1 is kernel of Fn. If this is exact at each Mn, then we say that it is an exact sequence. As I told you before, what is the kernel? Kernel of Fn means the set of all x such that Fnx equal to 0. See here. Suppose that consider the following diagram of R modules and R homomorphisms. Look into this diagram carefully because it is difficult to draw. I'm showing the picture of this what you call sequence of homomorphisms and sequence, exact sequence. See M to N, F is from M to N, G is from N to N, and M to M dash alpha, N to N dash beta, N to P dash gamma, and M dash to N dash is F dash, N dash to P dash is G dash. Look into these homomorphisms. R module and R modules and homomorphism. See here. F is a mapping from M to N. G is a mapping from N to N. F dash is a mapping from M dash to N dash. And G dash is a mapping from M dash to N dash to P dash. And alpha is a mapping from M to M dash. Beta is a mapping from N to N dash. And gamma is a mapping from N to P dash. Now let us see. This is a commutative and has exact rows. Then the following holds. See here, alpha, gamma, and G are epimorphisms. Epimorphism means alpha is onto homomorphism, gamma is onto homomorphism, G is onto homomorphism. Then definitely beta. Beta is also. Look into this diagram. Alpha and gamma, G. Alpha, gamma, G are epimorphisms. then beta is also epimorphism. Again, alpha, gamma, and f dash. See here, alpha, gamma, f dash are monomorphisms. Monomorphism means a one-one homomorphism. Then so is beta. If beta is epimorphism, f dash and gamma are monomorphisms, then alpha is an epimorphism. If beta is a monomorphism and alpha and G are epimorphisms, then gamma is a monomorphism. Students, here you mainly focus on three things. What is the homomorphism, epimorphism, and monomorphism? Homomorphism means homomorphism means, see here, alpha and gamma and G are epimorphisms. So beta is epimorphism. See here, alpha, gamma, and G are epimorphisms. Then beta also will become epimorphism. Again, alpha, see here, alpha, gamma, f dash. If these are monomorphisms, then also beta is a monomorphism. If beta is an epimorphism, then f dash and gamma are monomorphisms, then alpha is epimorphism. Just see here, we are studying when a homomorphism on R modules will become epimorphism and monomorphism. Proof is very simple. Here, given that alpha, gamma, G are epimorphisms. So we have to prove beta is epimorphism. Epimorphism means on to homomorphism. Already beta is a homomorphism only. So beta is a mapping from where to where? Here beta is a mapping from n to n dash. Beta is a mapping from n to n dash. You have to prove beta is onto means for every element in n dash there exists a pre-image. That means let y dash belongs to n dash. Then there exists G dash belongs to P, and since gamma is epimorphism, there is alpha belongs to P such that gamma, let's say y belongs to P such that gamma of y is equal to G dash y dash. Again, since G is epimorphism, there is y belongs to X such that G of y is see here it is not clear in the notes. So I'm writing on the whiteboard. You check once again. See, beta is a mapping from n to n dash. So we prove that beta is onto. There exists beta, let's take y dash belongs to n dash. I prove that this y dash has pre-image in n. Then definitely G dash of y belongs to P dash, and you have gamma is epimorphism. Gamma is epimorphism means you have some y belongs to P, you have gamma of y is equal to some G dash of y dash. Again, what is G? G is epimorphism. G is epimorphism means there exists y belongs to n such that G of y equal to y dash. So you have G of y equal to y dash. Now consider G dash of y dash. What is G dash of y dash? Y dash is G dash of y dash is gamma of y. Gamma of y. Gamma can be written as gamma circle G of y, which is nothing but G dash circle beta of y, which is G dash of beta y. Hence, you have y dash is equal to beta y, which belongs to kernel of g dash, which is nothing but image of f dash. Therefore, there is x dash belongs to m dash such that f dash of x dash is equal to y dash minus beta y. Y dash minus beta y. Again, since alpha is epimorphism, given alpha is epimorphism, there is x belongs to m. Alpha is from m to m. See, before proving this theorem, always you have to consider these points. You have f is from m to n. Okay, alpha is from m to m dash. Beta is from n to n dash. G is from n to n dash. G is from n to n only. Gamma is from n to p dash. F dash is from m dash to n dash. G dash is from n dash to p dash. N dash to p dash. So keeping these points, what is, focus on two things, what is given and what you have to prove. We prove that first point, what I want to prove, given alpha, gamma, g are onto. Alpha, gamma, g are onto. I prove that beta is onto. Beta n to n dash. So if I take y dash, I prove that it has a pre-image. Now x belongs to m such that alpha x is equal to x dash. Alpha m to m dash. X belongs to m, for x dash belongs to m dash. Now you have f dash circle alpha is equal to beta circle f. Hence we have beta of y plus f of x is equal to beta y plus beta of f of x, because beta is a homomorphism. So what is beta y? We have taken y dash. Y dash minus f dash of x dash plus f dash of alpha x, which can be written as y dash minus f dash of x dash minus alpha x, which is nothing but y dash. F dash, this is 0, no? That's why alpha x is x dash. So x dash minus alpha x is 0. This will become 0. So what you have? What do you mean by beta of y plus f of x is equal to y dash? Means y plus f of x belongs to n. Why? Because beta is a mapping from n to n dash. N to n dash. So you have y plus f of x is n. That means for every y dash, there is a pre-image y plus f of x such that beta of y plus f of x is equal to y dash. So beta is epimorphism. Now second one. See, suppose alpha, gamma, f are monomorphisms. Then we prove that beta is a monomorphism, means let y belongs to n such that beta y is 0. Then gamma of g of y is g dash of beta y. Why? Because just now we proved that gamma circle G is equal to G dash circle beta. That is G dash 0. This is 0. Since gamma is a monomorphism, G of y is 0 means you have kernel of G is nothing but image of F. And what do you mean by this? You have, since gamma is a monomorphism, G of y is 0. That means y belongs to kernel of G. Y belongs to kernel of G means G is image of F, no? So therefore, there is x belongs to M such that f of x is y. Now you have f dash circle alpha x is equal to beta circle f of x, which is beta y equal to 0. So mainly focus on the functions. Which function is whose domains and ranges. Again, suppose beta is an epimorphism and f dash and gamma are monomorphisms. We prove that alpha is epimorphism. Alpha is epimorphism means alpha is a mapping from n to n dash. Am I right? Alpha is a mapping from m to m dash. M to m dash means you start with one element in m dash. So let x dash belongs to m dash. Since f dash of x dash belongs to n dash and beta is epimorphism, there is y belongs to n such that beta y is equal to f dash of x naught. There x dash. So you have 0 equal to g dash circle f dash of x dash, which is g dash of beta y, that is gamma of g of y, and gamma is a monomorphism. You have g of y is 0. Again, y belongs to kernel G, that is image of f means there exists m, x belongs to m such that y is equal to f of x, and you have f dash of the similar way you can prove that since f is a homomorphism, since f dash is a monomorphism, you write like this: x dash of alpha x equal to 0. That means x dash minus alpha x. Okay. Therefore, alpha is onto. Now, next, let us discuss about the very important theorem of commutative algebra, which is known as 5 lemma. Students, if you want to prove 5 lemma or 9 lemma, be perfect with the concepts of functions. See here. A function f from close a to b is said to be 1, 1. If for every a1 comma a2 belongs to a, f of a1 equal to f of a2 implies a1 equal to a2. Or whenever f of a1 not equal to a2, f a1 not equal to a2. That is, distinct elements in a has distinct images in b. Onto means for every b belongs to b, there exists a belongs to a such that f of a equal to b. This is onto mapping. So if you know these concepts and always focus on two things, what is given and what you have to prove, then you will get how to prove. Now coming to 5 lemma. Students, take 5 minutes to spend 5 minutes for this 5 lemma. Statement only. See here. A, B, C, D, E, 5 sets. Why it is called 5 lemma? A, B, C, D, E. These are all modules and are modules. All of you understood the concept of module? C. Homomorphisms is commutative and has exact rows. See here. A to B, B to C, C to D, D to E, F, G, H, I. These are the mappings. Again, alpha, beta, gamma. Again, alpha, beta, gamma, delta. This is a delta, this is a nu, like this. Again, f dash, g dash, h dash, I dash. If you are able to draw this diagram perfectly, you will get some marks. Okay, F is a mapping from A to B. G is a mapping from C to D. D is a mapping from G is a mapping from B to C. H is a mapping from G to D. I is a mapping from D to E. Alpha is from A to A dash, B to B dash, C to C dash, D to D dash, E to E dash. If you are perfect with the above theorem, then only you will be able to do this 5 lemma. 5 sets will be there. 5 mappings will be there. Rows will be there. You have to remember this. Alpha is epimorphism. Alpha is epimorphism. Beta, comma, delta are monomorphisms. Then gamma is monomorphism. Monomorphism means you prove only one, that's all. Again, nu is monomorphism, beta and delta are epimorphism, then gamma is epimorphism. If alpha, beta, delta and nu are isomorphisms, then gamma is also isomorphism. What is an isomorphism? 1,1 onto homomorphic mapping is called an isomorphism. That is the reason always you should focus on revise some concepts of rings, homomorphisms. See, we are writing monomorphisms means epimorphism for AP, and for the sake of simplicity, we write GF for G circle F. Now let us prove one by one. Given alpha is AP, beta, gamma, beta, delta are monomorphisms. We prove gamma is monomorphism. Gamma is monomorphism means gamma is from where to where? C to C dash. Here, gamma is from C to C dash. So take, let C belongs to C such that gamma C is 0. Gamma C means delta H, delta HC. That is H dash gamma C is 0. That is HC is 0 because delta is 1,1. What do you mean by H of C is 0? H belongs to, sorry, C belongs to kernel of H. What is the kernel of H? Is image of G. Because these are all exact sequences. So you have C equal to G of B. That means you have G dash of beta B equal to gamma of G of B, which is gamma C 0. So beta of B belongs to kernel of G dash because G dash of beta B is 0. So you get beta of B belongs to kernel of G dash. Again, kernel of G dash is image of F dash. So what do you mean by this? Beta of B equal to F dash of A dash. So you have A dash is equal to alpha A. Why? Because alpha is epimorphism. Epimorphism means onto. Again, you have beta B equal to f dash of A dash. That is f dash of alpha A. Alpha A is nothing but beta f at A. So B equal to f of A, since beta is monomorphism. Ante entandi, you got C equal to G of B. C equal to G of B, which is equal to GF at A, which is equal to 0. Therefore, gamma is a monomorphism. Other two are very easy. So you can prove by above theorem also. Then the important one is 9 lemma. You will get one theorem for 10 marks, 9 lemma. Look into this diagram. Suppose that the following diagram of modules and homomorphisms is commutative and has exact rows. Exact rows, and suppose that middle column is also exact. Exact means, what do you mean by exact? Exact means image of the previous function is kernel of the preceding. Nine lemma. This is one of the important theorems of commutative algebra. Look into this diagram. F dash is a mapping from M dash to N dash. G dash is a mapping from N dash to P dash. F is a mapping from M to N. G is a mapping from N to P. F double dash is a mapping from M double dash to N double dash. G double dash is a mapping from N double dash to P double dash. Have a clear idea about this diagram. This is called 9 lemma. See, then the first column is exact. See here. First column is this one. Exact if and only if the last column is exact. Ante enti, first column is exact means if kernel of M dash is M. If and only if kernel of P is P dash. Hope you are following. First, suppose first column is exact. To prove that the third column is exact, we have to prove that gamma dash is monomorphism and image of gamma dash is kernel of gamma and gamma is epimorphism. These three things we have to prove. Listen carefully and try to digest the diagram, how it is given. What do you mean by sequence of exact sets? First, we prove that gamma dash is monomorphism. Gamma dash is a mapping from P dash to P. Gamma dash is a mapping from P dash to P. Take some y dash belongs to p dash. Here print was not good. Y dash belongs to p dash, so that gamma of y dash is 0. Since g dash is epimorphism, there exists y dash belongs to n dash, such that g dash of y dash, g dash of y dash equal to f dash, some element f dash. Now g of beta dash y dash is gamma of g dash of y dash. What is g dash of y dash? Some you take x dash, here you take x dash is 0. What do you mean by that? You got g of beta dash of y dash is 0. Means beta dash y dash belongs to kernel of G. What is the kernel of G? Kernel of G is image of F. Am I right? Kernel of G is image of F. Look into second row. They are exact rows. Rows are exact. We have to prove that columns are exact. We prove that first column is exact if and only if third column is exact. So therefore, there exists x belongs to M such that f of x is equal to beta dash y dash. Consider f double dash of alpha x, which is equal to beta of f of x minus, which is equal to beta into beta dash of y dash, because f of x is beta dash of y dash. So this is 0. Ante f double dash of alpha x is 0. And that means, see here, f double dash of alpha x is 0. Ante you take f double dash of 0, since it is monomorphism, you get alpha x equal to 0. Whenever alpha x is 0, x belongs to kernel of alpha. What is the kernel of alpha from the diagram? Kernel of alpha is image of alpha dash. Image of alpha dash. We can choose x dash belongs to m dash such that alpha dash into x dash is x. Now since beta dash of y dash is f of x means f of alpha dash x dash. In place of x put alpha dash x dash, which is beta dash of f dash of x dash. Again beta dash is monomorphism. You have y dash. See here, you have beta dash of y dash is beta dash of f dash of x dash, and beta dash is 1 1 means images are equal. Y dash is equal to f dash of x dash. Therefore, z dash is equal to g dash of y dash, which is g dash of f dash x dash 0. That means gamma dash is monomorphism. Then what we have to prove? We prove image of gamma dash is kernel of gamma. Then only third row will become we prove that kernel of gamma dash is kernel of gamma. This I am writing on the whiteboard, and once you check. Let some x dash belongs to p dash. Let x dash belongs to p dash, and you have g dash is epimorphism. G dash is epimorphism. So you can choose y dash belongs to n dash. What is the G dash? G dash is a mapping from N dash to P dash. G dash is epimorphism from N dash to P dash. Y dash belongs to P dash. So their exits Y dash belongs to N dash such that G dash of Y dash is equal to X dash. Now you have gamma circle gamma dash of X dash is gamma circle gamma dash of G dash of Y dash is equal to gamma circle G circle beta dash of Y dash is equal to 0. That means you have beta circle beta dash is 0. What do you mean? That means image of gamma dash is a subset of kernel of gamma. And again, we prove that kernel of gamma is a subset of image of gamma. Suppose you take one element in kernel of gamma. Since G is epimorphism, there exists Y belongs to kernel of gamma such that G of Y is equal to 0. That is G double dash of beta Y is equal to gamma G of Y, which is equal to gamma of 0, 0. That is beta Y belongs to kernel of G double dash. Kernel of G double dash is nothing but image of F double dash. Beta Y belongs to kernel of G double dash, which is equal to image of F dash. So therefore, there exists X double dash belongs to M double dash such that F double dash of X double dash is 0. Since alpha is epimorphism, there is X belongs to M such that alpha X is equal to X double dash. So beta Y is equal to F double dash of X double dash, which is equal to F double dash of alpha X minus beta of F of X. That means beta Y minus F of X belongs to kernel of beta, which is image of beta dash. So therefore, you have G of Y is equal to G of Y minus, Therefore, you have beta dash of Y dash is equal to Y minus F of X, which is G of Y, that is G of Y minus G of F of X, that is G of Y minus F of X. So which is nothing but gamma dash of G dash of Y dash. Therefore, you have X double dash belongs to image of gamma dash. No, Y dash, What we have to prove here, you have already we proved that image of gamma dash is subset of kernel of gamma. Then we have to prove that kernel of gamma is a subset of image of gamma dash. So correct only. You have Y dash belongs to image of gamma dash. Therefore, image of gamma dash is kernel of gamma. So converse is also same. Students, this is called 9 lemma, which states that statement is also very important, which states that if there is a diagram given by modules and homomorphisms is commutative and has exact rows, and suppose that middle column is exact. Middle column already it is given exact. That means you have kernel of image of beta is kernel of beta dash. Then the first column is exact if and only if last column is exact. So this is known as 9 lemma. Next, I want to prove one more important theorem of important concept of commutative algebra, which is lying over theorem and going up theorem. These three are important theorems of commutative algebra. Let T be extension of a ring R, an ideal J of T. What do you mean by ideal? We say that a non-empty set S, R is a commutative ring with unity. We say that an ideal S, a subring, is said to be an ideal if for R belongs to R, S belongs to S, RS, SR belongs to S. Then we say that S is an ideal. Let T be an extension of ring R. An ideal J of T is said to lie over an ideal I of R if I is equal to J intersection R, which is nothing but J intersection R is contraction of J in R. What we say? J is an ideal, T is extension of ring R. If J intersection R is I, J intersection R is I. If it is J, this is R, then R intersection J is I. If you take like that, then we say that J lies over ideal I. J lies inside the ideal I. So this is called lying over theorem. See here. Let T be an integral extension of a ring R and let P be a prime ideal of R. We know that what is a prime ideal? AB belongs to P implies either A belongs to P or B belongs to P. Either A belongs to P or B belongs to P. And we know that it is an integral domain if and only if R by S is an integral domain. P is a prime ideal or S is a prime ideal if and only if R by S is an integral domain. Let T be an integral extension of a ring R and P be a prime ideal of R. Then there exists a prime ideal Q of T lying over P. That is Q intersection R is P. Try to understand the concept clearly. Lying over theorem. When do you say that an ideal? See here, an ideal J lie over an ideal I. An ideal J lie over an ideal I if I is equal to J intersection R. If I equal to J intersection R, then we say that if I is equal to J intersection R, then we say that J lie over an ideal I. So let T be an integral extension of a ring R and let P be a prime ideal of R. Then there exists a prime ideal Q of T lying over P. That is, there exists a prime ideal Q such that Q intersection R is P. Q intersection R is P, which is known as lying over theorem. So for our convenience, write S equal to R minus P. Since P is a prime ideal of R, S is a multiplicative set in R, we have multiplicative set in T also. So write tau is equal to set of all I such that I is an ideal of T and I intersection S is empty. Since 0 not belongs to S, you have 0 belongs to tau and this tau is non-empty. So clearly tau is a partially ordered set with respect to set inclusion. Let I alpha belongs to delta be a chain in tau. Clearly I is equal to union I alpha. We know that the union of set of ideals is an ideal. And what is S intersection I? S intersection I is S intersection union I alpha, or union alpha belongs to delta S intersection I alpha, which is empty. So by John's lemma, there exists a maximum element, say Q. So that is nothing but your 1 minute. Maximal element say Q, that Q intersection R is your P. Then going up theorem. See, let T be an extension of a ring R and let R be the integral closure of R in T. All this it is not required. Just I want to prove going up theorem. What is going up theorem? Let T be an integral extension of a ring R and let P1, comma P be the prime ideals in R such that P1 is a subset of P. If Q1 is a prime ideal of T lying over P1, then there exists a prime ideal Q such that Q1 is a subset of Q and Q lies over P. Students, look into the proof of this. Let Q1 be a prime ideal. Let Q1 be a prime ideal of P lying over P1. So write S equal to R minus P. Since P is a prime ideal of R, S is a multiplicative set in R. So S is a multiplicative set in T. So since Q1 intersection R is P1, which is a subset of P, you have Q1 intersection R is subset of P. So you have Q1 intersection S is empty. So this is going up theorem. So concentrate on these concepts. And as today is the last class, let us discuss about Artinian and Noetherian rings. Let us discuss about a R module is Noetherian and Artinian. See here, we know about the partially ordered set. What is a partially ordered set? P is any non-empty set with the binary relation less than or equal to. We say that P is a partially ordered set if less than or equal to is reflexive, antisymmetric, and transitive. It is antisymmetric and transitive. And we know that we know about upper bounds and lower bounds, infimum, supremum concepts. You students, you have to remember two concepts. You have element is less than the upper bound. Upper bound is less than supremum. Sorry. No. Element, sorry. Not like. We have element is less than supremum. Supremum is less than or equal to upper bound. Again, element is greater than infimum. Infimum is greater than or equal to lower bound. And we know that two elements in a partially ordered set are said to be comparable if either A less than or equal to B or B less than or equal to A, then we say that two elements are comparable. And we know that what is the maximum element if there is no element greater than that. When you say that an element is minimal element, it is a minimal element of a set if there is no element which is less than that. What is John's lemma? Every chain, if every chain is a poset which has upper bound, which contains a maximal element. Similarly, it has a lower bound, contains a minimal element. Like completeness property of real numbers, we know that every set of real numbers which is bounded above has a supremum, which is bounded below has infimum. Here also, John's lemma states that if it has a upper bound means it has a maximum element. Otherwise, it will have a minimal element. Now, we say that a poset P less than or equal to is set to satisfy first one, ascending chain condition. Ascending chain condition or ACC, ascending chain condition. If every ascending chain, what do you mean by ascending chain? Increasing chain, x1 less than, x2 less than or equal to, so on, is stationary. Is stationary. Stationary means that is there exists a positive integer n such that xn equal to xn plus 1, so on. Similarly, descending chain condition. Descending chain condition means x1 greater than or equal to, x2 greater than or equal to, so on. That is what we call ascending chain is stationary. We say that it satisfies ascending chain condition. If descending chain condition is stationary, then we say that it satisfies descending chain condition. Maximal condition, if every non-empty set of P contains a maximal element. Maximal condition means every non-empty subset of P contains a maximal element. Minimal condition means every non-empty set of P contains a minimal element. Okay, Andy? So see here, you have to remember two more points. That is, a partially ordered set satisfies ascending chain condition if and only if P satisfies maximal condition. And partially ordered set satisfies descending chain condition if and only if P satisfies minimal condition. And a poset or a partially ordered set is said to be Noetherian if it satisfies ascending chain condition. You remember, ascending chain condition means every ascending chain is stationary. Stationary means after some values they will become equal. Descending chain condition means x1 greater than or equal to, x2 greater than or equal to, etc. implies xn equal to xn plus 1 and so on. Then do you say that partially ordered set contains ascending chain condition if it satisfies maximal condition? When you say that a partially ordered set satisfies descending chain condition if it satisfies minimal condition. A partially ordered set is said to be Noetherian if it satisfies ascending chain condition. Artinian if it satisfies a descending chain condition. Or in other words, I told you, just now we told that a partially ordered set satisfies ascending chain condition if and only if it satisfies maximal condition. So it satisfies maximal condition then the partially ordered set contains Noetherian, is said to be Noetherian. Otherwise, it is Artinian. On these concepts, you learn two theorems, or same thing we can imply to modules also. A module M is said to be Noetherian module if it satisfies ascending chain condition. A module M is said to be Artinian if M satisfies a descending chain condition. If you take any finite dimensional vector space, all of you know finite dimensional vector space. It has finite number of elements in the basis that span V. So every finite dimensional vector space is both Noetherian and Artinian. And we say that an R module M is Noetherian if and only if M satisfies maximal condition. And also we say that an R module is Noetherian if and only if every submodule of M is finitely generated. So with this, we are stopping this course, Commutative Algebra. Students, all the best for your exam and prepare systematically. Take one unit, prepare for important questions.